Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Fraunhofer diffraction at double slit. Let's begin. Let a parallel beam of monochromatic light having wavelength lambda of monochromatic light is incident normally on two rectangular slits. A double slit A, B, C, D. Here we place the screen. Center at O. The parallel beam of light having wavelength lambda is incident normally on that of rectangular slits A, B, C, D. These are placed very close and parallel to each other. Let the width of each slits A be the width of each slit, here also A, and the distance between the two slits, let me take the portion, the opaque portion, let small b. Width of A is the width of each slit. Distance between the two slits is equal to A plus B, with the distance between two slits. Here we place a convex lens as we treat with Fraunhofer type of diffraction. So the convex lens is placed very close to that of slit. The rays parallelly come to that of slit are focused on O at O means the screen is placed on the focal plane of that of convex lens L. Let another point which is Q on that of screen, and the rays which are diffracted at an angle theta after diffraction, they are focused on the point Q. So, we obtain a diffraction pattern on that of screen. Again, look these two slits, here slit 1, that one be slit 2. Each slit act as a coherent source. These two slits act as a coherent source. Therefore, due to this coherent source, we obtain also an interference pattern on that of screen. So, in Fraunhofer diffraction at double slit, the diffraction pattern that are observed on that of screen basically contains the diffraction pattern as well as the interference pattern. Let me mathematically treat how the intensities are distributed on the screen due to Fraunhofer diffraction at double slit. For that purpose, first we have to calculate the path difference between any two corresponding rays. Draw a perpendicular from the point A to the wave from C. Let that point be N. Here the angle is theta. So, the path difference between two corresponding rays can be calculated. In case of Fraunhofer type of diffraction, the incident wavefront is a plane wavefront as the light rays coming from infinity. The path difference is equal to Cn with the path difference Cn is equal to that length A plus B angle sin theta. As we know from right angled triangle ANC sin of theta is equal to A plus B sin of theta is equal to Cn divided by AC, or Cn is equal to AC sin theta. Here AC is equal to A plus B, which is the distance between the two slits. A plus B sin theta, that be the path difference. Now, the phase difference in between them phase difference is equal to 2 pi by lambda into path difference. That will be the relation between phase difference and path difference. Let us say phase difference be delta is equal to 2 pi by lambda path difference a plus b sin theta. Let us say which is equal to 2 beta, or delta is equal to 2 pi by lambda a plus b sin theta is equal to 2 beta let. From the theory of diffraction at single slit, the resultant amplitude due to the secondary wavelets diffracted from each slit is A sin alpha by alpha. Now we know, let I prefer it as path difference as equation number 1, that be equation number 2. We know that from diffraction at a single slit, the resultant amplitude that is diffracted, the resultant amplitude is A sin alpha by alpha. Where A is a constant and alpha is equal to pi A sin theta divided by lambda. That is the resultant amplitude for single slit. Here the two slits are equivalent to two coherent sources, and each sending a wavelength having the amplitude A sin alpha by alpha in the direction of theta. Consequently, the resultant at point Q can be calculated by taking vector addition rule. Here we consider the two slits are equivalent to two coherent sources and each sending a wavelet of amplitude A sin alpha by alpha. Each is a single slit. From each, the wavelet having the amplitude A sin alpha by alpha in the direction of theta. Pointed on that of screen Q. So, the resultant amplitude at point Q will be the resultant interference between the two waves. Therefore, the resultant amplitude at point Q due to the resultant interference at that point. So, the resultant amplitude of these two waves from these two slits, and these are calculated at point Q. So, we plot vector addition method. Here the amplitude let A sin alpha by alpha, another wave having the amplitude A sin alpha by alpha. Here the phase angle, the delta be the angle in between these two, and the resultant R. Therefore, the resultant amplitude R at Q can be obtained of vector addition of amplitude. Vector addition of amplitude. From that of figure, OB square is equal to OA square plus AB square plus 2OA AB, angle between them cos delta. Therefore, R square is equal to A sin alpha by alpha square plus A sin alpha by alpha square plus 2 A sin alpha by alpha A sin alpha by alpha into cos delta is equal to 2A square sin square alpha divided by alpha square plus 2A square sin square alpha divided by alpha square cos delta. Here A square sin square alpha divided by alpha square, here A square sin square alpha divided by alpha square. Adding these two, 2A square sin square alpha divided by alpha square. From these, 2A square sin square alpha divided by alpha square cos delta. Cos delta using the trigonometry formula, 2A square sin square alpha divided by alpha square taking common, we have 1 plus cos delta 2 a square sin square alpha divided alpha square. We use the trigonometry formula as 2 cos square delta by 2, which is equal to 1 plus cos delta, as cos square delta by 2 is equal to 1 plus cos delta divided by 2, again multiplying a 2 here, so 2 to cancel out, we have 1 plus cos delta. Now simplifying that one, we have r square is equal to 4 a square sin square alpha divided by alpha square cos square beta, that be the r is the resultant intensity, sorry, that is the resultant amplitude. From that resultant amplitude we can calculate what be the resultant intensity at point Q. The relation between intensity and amplitude, the resultant intensity I, which is directly proportional to the resultant amplitude, square of resultant amplitude, or I is equal to, using a proportionality constant, k r square, where k is the proportionality constant which is equal to 1. Therefore I is equal to r square. So resultant intensity I is equal to the value of r square, 4 a square sin square alpha divided alpha square into cos square beta, 4 a square sin square alpha divided by alpha square into cos square beta, which is the resultant intensity. Look at that particular equation carefully. Equation number, here equation number 3, here equation number 4. That term a square sin square alpha divided by alpha square, a square sin square alpha divided by alpha square, which is basically we derive in case of intensity distribution from single slit, a square sin square alpha by alpha square, that be the intensity, that due to diffraction. And this term cos square beta, the term cos square beta due to interference. As I first mentioned, in Fraunhofer diffraction at double slit, the diffraction pattern we observe on the screen due to diffraction as well as due to interference. That term basically for diffraction, that term basically for interference. Now from that expression we can easily calculate the condition for central right, secondary maximas and minimas, as well as intensity distribution. The dependence of intensity of that term a square sin square alpha divided by alpha square due to diffraction term. From diffraction we know the pattern as central maximum or principal maximum and secondary maximas and minimas named like first secondary maxima, first secondary minima and so on. The term a square sin square alpha divided by alpha square gives principal maximum in direction theta is equal to 0, which corresponds to point P on the screen, point O on the screen. Come to the figure. In that figure, at point O we have the central maximum. Again from the expression also, here the angle theta will be 0. These rays are parallel. At point O we achieve central maximum. Again that is clarified from expression. The term a square sin square alpha divided by alpha square, we have maximum intensity. For what? That interference term having maximum means the value of cos will be maximum. Here cos square beta is equal to 1. Next, the term a not equal to 0. Therefore, the term alpha must be equal to 0. The term alpha, when the value of alpha is 0, we have maximum intensity. Again we know the value of alpha, which is equal to pi a sin theta by lambda. Therefore sin of theta is equal to 0. Therefore theta is equal to 0. When the value of theta is equal to 0, then we achieve the principal maximum. So the condition for principal maximum, that is clearly observed in case of figure, as well as from that of expression we easily clarify the condition for principal maximum. Next, secondary minimas and maximas. Next, the minimas are obtained in direction given by sin alpha nearly equal to 0. The intensity will be minimum when that sin term will be minimum. Minimum value of sin is equal to 0. Generalizing the value of alpha is equal to plus minus m pi. Value of alpha pi a sin theta divided by lambda is equal to plus minus m pi. Or a sin theta, pi pi cancel out, a sin theta is equal to plus minus m lambda, where m starting from 1, 2, 3 dot dot dot, but excluding 0. When m is equal to 0, we have the central maximum term. That be the condition for minima. when the path difference a sin theta is the path difference is integral multiple of lambda, then we achieve the minimas. Next, the position of similarly the position of secondary maximas, the secondary minimas, here are the secondary minimas, secondary minima. Similarly, the position of secondary maxima due to this term are at alpha is equal to plus minus 2m plus 1 pi by 2. Putting the values of alpha, pi a sin theta by lambda is equal to plus minus 2m plus 1 pi by 2, pi by cancel out. So, a sin theta is equal to plus minus 2m plus 1 pi by 2, pi by cancel out, sorry, lambda by 2, lambda by 2. Again m stands for 1, 2, 3 like this. When the path difference is odd multiple of lambda by 2, we have secondary maximas. These are the respective conditions that are derived from that of diffraction term a square sin square alpha by alpha square. Here is the principal maxima, secondary minimas and secondary maxima. Let we show it graphically. When we plot the graph, when graph is plotted, the intensity and alpha, here alpha is equal to 0, then pi, 2 pi and 3 pi, minus pi, minus 2 pi, minus 3 pi, the term a square. That is sin square alpha divided by alpha square. Now the amplitude a square. The intensity distribution due to the term a square sin square alpha by alpha square. A square, that is the capital A square. Okay. Next, due to interference term cos square beta. Now, dependence of intensity, dependence of intensity on cos square beta. How cos square beta term is responsible for this pattern. Here cos square beta, the interference term cos square beta gives the set of equidistant dark and bright fringes. So, the bright fringes maximas are obtained, the bright fringes which is named as maxima are obtained in the direction given by cos square beta is equal to 1 or beta is equal to plus minus n pi, where n stands for 0, 1, 2, 3 like this, and the value of beta say here delta is equal to 2 pi by lambda 1 plus b sin theta is equal to 2 beta. So, beta is equal to 2 to cancel out pi by lambda a plus b sin theta. The value of beta is put here, that is pi by lambda a plus b sin theta is equal to plus minus n pi. Pi by cancel out, we have a plus b sin theta is equal to plus minus n lambda, where n stands for 0, 1, 2, 3 dot dot dot. So, the various maximas corresponds to n is equal to 0, n is equal to 1 and n is equal to 3 like this, and the interference pattern we observe here. The interference pattern, if we plot the graph, the intensity and beta 0, pi, 2 pi, 3 pi, pi, 2 pi and 3 pi. The figures are looking like this. Alternate dark and bright fringes are obtained having equal distances. These are the interference pattern we see due to that particular term cos square beta. Now, when we combine these two figures due to the diffraction term and due to the interference term, and finally what should be the diffraction pattern we observe in case of Fraunhofer diffraction or double slit on the screen, combining these two intensity distributions, we have finally achieved the intensity distribution as here the intensity due to diffraction and interference. So, the figures are looking like when we combining the diffraction and interference, we see just like the intensity distribution. This is the intensity distribution here at point O. That is the intensity distribution due to double slit, So, with the help of this video lecture, we understand Fraunhofer type of diffraction at double slit. First we calculate path difference, then phase difference, taking these two slits as the coherent sources. So each having the amplitude A sin alpha by alpha, and resultant amplitude can be calculated by vector addition rule. The relation between amplitude and intensity, so the resultant intensity is that given expression, so which is the combination of both diffraction as well as interference. So the dependence of intensity due to that diffraction term, which gives rise to principal maximum condition, secondary minima condition and secondary maxima condition. From that we put forward the distribution of intensities due to that diffraction term. Again the dependence of that interference term cos square beta, the dependence of the intensity on cos square beta, we have that condition basically for maximas and minimas. So the intensity distribution having the equidistance, alternate dark and bright fringes are obtained in case of interference pattern. So combining these two, due to diffraction as well as interference, we have the intensity distribution pattern just like this, which is the intensity distribution due to Fraunhofer diffraction at double slit due to the combination of both diffraction as well as interference. So with these useful and informative notes, let me wind up this session. Thank you.